keep an eye on it. Tried to figure out how to make it beep when it shuts off, but I couldn't. So let me write these down. And I'll leave the red ones for you to use as practice. Let me keep all that. But I'll put these on D2L, 6.19, 20. Maybe we can get to all those, we'll see. So 6.19, I'll do 2.0. This should look exactly like it did before. So I'm really just reiterating here. What is the frequency when the wavelength is 0.86 nanometers? So what is the frequency? We'll use this. So we're looking for the frequency. We have the wavelength. We're going to use the speed of light. 10 to the 17 nanometers over. Three divided by 0.86. $3.7209 is what my calculator says. We're going to be at two significant figures. Your book actually did put 2 zeros here. Two, so it's the 3 and the 4, so 5. I shouldn't have put nanometers there. Nanometers per second. Yeah, frequency. That should be the answer to that. We just land in standard scientific notation. So now we frequency, and we want to go to a wavelength, 6.4 times 10 to 11. This is B. I'm doing 6.20. The first one was A, this is B now. The frequency. 6.4 times 10 to the 11. Over S. Using this again, and it's going to be a little bit of algebra, you can do that. So again, we're going to go 3.00 times 10 to the 17 nanometers per second divided by 6.4 times 10 to the 11, 1 over S. And we'll end in nanometers. If you just look at the units, if I take this and move it up to the top, I invert it. So the units, once I do that, the units look like this. If I invert that, I have S over 1. The S's cancel and we end at nanometers. So we are going to end in nanometers. 3.00 divided by 6.4 times 10 to the 17. I'm going to move this 10 power of 10 to the top, so it's become 10 to the negative 11. So this numerical part, that's what my calculator gives me. 17 minus 11, 10 to the 6. Two significant figures, so I'm really going to go 0.47 times 10 to the 6 nanometers. And if I want that in standard scientific notation, I'll probably ask you to do that on the test for all these. We would have 4.7 times 10 to the 5. 10 to the 6, 10 to the 5. So that would be the answer for the wavelength. That would be, okay. What is the wavelength of radiation? Okay, C is saying, would A or part B be detected by an X-ray detector? All right, let's just use this. We could have answered that question just by looking at this. A is 0.86. Nanometers as a wavelength, and B is 6.4 times 10 to the 11. One over S. I told you I'll give you this on the test. Which one would be detected by an X-ray detector? So we're looking for X-ray. This has wavelength in meters. So instead of nanometers, I'm going to shove the M over here. Nano means 10 to the 9, 0.86. Maybe I should say 8.6, because it's really this we look at on this chart. So we're into the 10 to the 8, 10 to the 8 range in meters for A. Negative 9. 10 to the negative 9 meters. So we're in the 10 to the negative 9 area. So that puts us in X-rays. This one is the 10 to the 11 on frequency per second. 10 to the 11 would put us in infrared. So this one, A, is X-ray, and this one is infrared. You follow that? Being able to read this chart. The chart is in meters, so you'll have to think about this, because most of what we do for wavelength shows up as nanometers, at least for our work, because that's the visible range. It tends to be what we do in the lab, but spectroscopy can look at all of these. But what we will do in lab is looking at colors. All right. Go back to here. There was one more question in 20. picoseconds. To solve that, photons, electromagnetic radiation travels. I think this would be easier. This is c, speed of light, 3.00 times 10 to the 8 meters per second. We changed it to 17 so we could use nanometers, but I'll write it like this, meters in 1 second, picometers. So actually I have to do this. In 1 second, it travels distance. It doesn't tell us what units, so we're going to end up in meters the way I'm doing this. No, I had it right. Picoseconds, is that what it says? Picoseconds. Picoseconds. 1 second is 10 to the 12 picoseconds. I'm still brain dead, apparently. I'd rather do this. Ten to the negative 12 seconds is 1 picosecond. That'll do it. That'll give us an answer in meters. How far does it travel? But I'll set it up. 3 times 0.38. This part is 1.14. That's what my calculator says, but really it's 1.1 because of 2 significant figures. 1.1 times 8 minus 12 is 10 to the negative 4. That's the answer. How far it travels. What else do I have? 21 and 22. So 21 is you solving for frequency. When it says predict the color, you can predict the color just from looking here. 650 nanometers. That's, so let's do this. Nanometers. So I'm going to push the meters out here and then turn the N into times 10 to the 9. And then you see what I did there? That's going to give us the ability to read 10 to the 11 meters on the scale. What was this? Meters. 10 to the -9, 10 to the -11. That's not right. 987. Okay. Now do you see what I did there? Now that I did it correctly? So we're looking around here. So it's in the ultraviolet. Oh, no. Did it say what color? Check myself here. What am I doing? This was 21. Predict the color. 650 nanometers, 10 to the -9, 10 to the -7. If I ask you this on a test, it'll be more straightforward. But I guess you just say purple.
The spectrum of visible region is given in nanometers.
Oh, so 650 would be about here, red? I don't know. I'm looking here, and 10 to the -7 is definitely, so this is 10 to the -6 right here. -5. All right, yeah, he's right. You just read the bottom scale. 650 here, so it'd be red. No. Something's weird about their calculations, but thank you. If I'm just going to go brain dead this long into class, that was 21. Let's see what 25 is. All right, but I'll do 26. Yes. Okay, green laser. Yeah. Leaving, came back at, that's all I could do in 25 minutes, good Lord. Let me go ahead and I'll do some more of these on Tuesday, because we're actually going to do this lab on Tuesday, but let me do one more on these transitions. Let me at least set it up for you. So 39 and 40. Consider the transition from n equals 4 to n equals 9. Oh yeah, I should have said this. Let me say this. I know we're about out of time. So if this is n equals 9 and this is n equals 8, and this is saying a transition, so it's 40, 41, 40. It goes from 4 to number 9. So now we're talking about a transition where it goes up. And I've almost exclusively talked about transitions that go down, and then the photon that comes out. Photons that come in, so there's a particular amount of energy that's associated with that transition. Therefore, a particular frequency, therefore a particular wavelength. Same from a transition from here to here, or here to here, or here to here, whatever the energy is. But an energy that would correspond to a jump from there to, say, here, you can have a photon that has that amount of energy that comes in and hits the atom. But unless it's one of those perfect, unless it's exactly between here and here, or the energy is the gap between here and here, unless it's exactly one of those, it's just going to bounce away. I didn't say that already. But atoms can't absorb just any frequency. They have to absorb a particular frequency that corresponds to the energy gaps. So really, when you're looking at something like this, and you see green, this absorbs a lot of different wavelengths. And other wavelengths it bounces out. What you're seeing is the light that bounces out of this, not the light that it absorbs. So it won't absorb a photon unless it's got an energy of that gap, or maybe that gap, or that gap. But it's got to be one of those gaps. It can't be somewhere in between. That's what leads to those line spectra. So what I didn't say is that when you hit an atom with light, it has to be a specific frequency, or there's a set of frequencies that it'll absorb and then do the transition. But if somewhere in between, the light just bounces away, which is kind of weird. But anyway, I didn't say that already, but you can calculate so the delta E here will be positive because that comes in and it absorbs and it goes from, it's telling you it goes from there to there. I know we're out of time, but so the atom absorbs a little energy when it does that, and it loses that energy when it drops back down. We'll do some more of these Tuesday. I've got more to do in this chapter anyway. But start practicing some of these using these equations. I meant to give you some that involve these as well, and that's what these are. So. We'll go over those again. Maybe not these, but practice some of those before Tuesday. All right. Yeah, I'll just stop there.